Hey, super scientists, we're looking at page 6 in your lab notebook, and we're going to be talking about isotopes. Take a look at this picture here. So you have a glass of water, and you have some ice cubes in it. But notice there are some ice cubes at the top and some ice cubes at the bottom. Think about when you usually make a glass of water or a glass of tea, a glass of Coke, and you put some ice cubes in there. Where do the ice cubes usually go? You usually see them floating at the top, right? So think about that for a minute. Why might you have ice cubes at the top and the bottom in a cup of drink that you might have? So we're looking at isotopes, and isotopes are atoms of a same element, so they're going to have the same number of protons, but they have a different number of neutrons. So we know that when we look at the periodic table and we examine the information that's provided in each box, that we are given the atomic number, which tells us the number of protons, and also the number of electrons, and we can find the number of neutrons by finding the mass number. So we round the atomic mass to a whole number, and then that gives us the mass number. That mass number minus atomic number is going to give us the number of neutrons. So when we determine the number of neutrons for hydrogen by using the information in the periodic table, we end up not having any neutrons. So look at this protium here. This is the form that we're most familiar with. That is only going to have one proton and one electron, no neutrons, because mass number of 1 minus atomic number of 1 is 0, so no neutrons. Then you have deuterium. This one is going to be an isotope of hydrogen. It's got a neutron. And this is another isotope of hydrogen, tritium, and this has 2 neutrons. So when you have isotopes of different elements, sometimes they are unstable, sometimes they are radioactive, sometimes they're found naturally, and sometimes they can be created in laboratories as well. Here's some different isotopes of carbon. So you have on your paper this information here. Notice I already have the electrons on there for you. We have 1, 2, 3, 4, 5, 6 electrons on our orbital shells. That's because our atomic number is 6, which means that we're going to have 6 protons and also 6 electrons. So let's go through the information that we have. We have our 6 protons. We have 6 neutrons because 12.01 rounded to a whole number gives us our mass number of 12. So if we do 12 minus 6, that gives us 6. That's how we get this number of neutrons. And then our number of electrons, again, is 6. And that's what's presented for you already on the orbital shells. We're going to go ahead and put in the nucleus our 6 protons. That is represented by these blue circles with the plus sign in them. So you can see there's 6 already there. And we're going to draw in the neutrons. Now I've chosen just to draw the neutrons as open circles, and I just shaded them in yellow so you could see the difference between the 2 different subatomic particles that are in the nucleus. So that information that's provided for our Bohr model of carbon, this is basically the same as you have here. So we have our 6 protons, our 6 neutrons. So if we add up the protons plus the neutrons, that gives us the mass number. 6 plus 6 equals 12. Mass number is 12. That's basically just the reverse of what we did a few minutes ago in order to determine the number of neutrons. So we already know that the atomic mass is 12.01, so that rounds to a mass number of 12. So that's why you can do 12 minus 6 gives you 6. To find out the number of neutrons. So this is the carbon atom that is presented to us on the periodic table. That's carbon 12. So now we have carbon 13. This is an isotope of carbon. So we're looking at the same information from the periodic table. Now if you've got an isotope of carbon, it's going to have just a number of neutrons that's different. The number of protons is the same, number of electrons is the same. It's the neutrons that will be different for an isotope. So this is the Bohr model we were just looking at. So instead of having our 6 neutrons, an isotope of carbon that's carbon 13 is going to have 7 neutrons. So to find the mass number, we're adding our 6 protons plus our 7 neutrons, and that's not 12, that is 13 now. So that isn't the number that we initially had. It now becomes 13. And that's why it's called carbon 13, because it's a reference to the amount of subatomic particles in the nucleus. So our protons, again, it's going to be 6. Protons doesn't change. Neutron changes. That's now 7. And our electron stays the same. So in order to present that in our Bohr model, we're going to have 1, 2, 3, 4, 5, 6 positive protons. And then we're going to have 1, 2, 3, 4, 5, 6, 7 neutrons. So notice that our original carbon atom right here, same number of electrons in the orbital shells, same number of protons, but the number of neutrons that you have presented in the nucleus is different. So it's just the number of neutrons that's different in an isotope. Here's our last example. This is carbon-14. Carbon-14 is radioactive. It's actually used to determine the age of rocks, of igneous rocks, and fossils that might be contained in different rock layers. So we're going to talk later about carbon dating and radioactive dating. So here's the example that we are continuing to look at. This is our carbon-12. That is our normal carbon atom straight from the periodic table based on this information. So in order to determine the information about carbon-14, we know that we still have our 6 protons. It's still the same thing. Our number of neutrons is going to be different. Since it's carbon-14, that 14 is a reference to the mass number. So instead of being 6 neutrons, we have 8 neutrons. So 6 plus 8 is going to give us our 14. So it's no longer carbon-12. It's not 6 plus 6 equals 12. It's 6 plus 8, which gives us our 14 as the mass number. So that's referring to the nucleus. So if we look at our information over here, protons 6, neutrons 8, electrons 6, and presenting that in our nucleus, we have 1, 2, 3, 4, 5, 6. So the number of protons has not changed. The number of neutrons, 1, 2, 3, 4, 5, 6, 7, 8. Number of neutrons is larger. So carbon-14 is an isotope of carbon that instead of having 6 neutrons has 8 neutrons. So isotopes, again, have the same number of protons but a different number of neutrons. So these 2 isotopes of hydrogen are ones that we had looked at earlier. And now if we'll look at our picture that we were looking at, now that you know about isotopes, why do you think you have some ice floating at the top and some ice floating at the bottom? Well, that's a great question, Ms. Owens. Thanks for asking. So the ice at the top, this is our normal ice. This is our ice that's going to be using this standard isotope of hydrogen, protium that we're most familiar with straight from the periodic table. And this is what the caption here is referring to as heavy ice. So the heavy ice on the bottom, what do you think was used instead of protium? Probably one of these isotopes. So one of your isotopes, deuterium, is going to be used to create this heavy ice, which when it's put in water, as you can see here, is more dense than the water. And that's because the mass has increased. The mass of that hydrogen atom has increased because of having that additional neutron. So now let's look at synthetic versus natural. This is on page 11 in your lab notebook. So some isotopes can be synthetic. That means that they're going to be man-made. They're going to be created in laboratory. So synthetic is just man-made, literally using your stems. Syn means together and the means put. So it's put together. And natural is going to be referring to something that's naturally occurring, an element that is naturally found in the earth or on the earth in some way. And I've just got a couple different examples here that you can kind of look at, some things that are natural versus synthetic that you may be familiar with. On your periodic table, most of the actinides are going to be synthetic, and I've shaded them in red here just so you can kind of see that. Basically above the atomic number of 92, uranium and above, is going to be synthetic. So all these are going to be created in laboratories. And you notice that the atomic mass is also in parentheses, and that's because a lot of these elements, when they're created in particle accelerators, they are so unstable that they decay really quickly. Their half-life is really fast, even just a matter of seconds. Or not even an entire second. So they decay really quickly, and they may not have additional isotopes that have been studied because of that. Let's look at a couple different things that are synthetic or natural that you may be familiar with. Salt. Salt is natural. Salt is found in the ocean. Sodium chloride. Air. Lots of different things in the air. We know there's nitrogen, there's oxygen, there's lots of other elements that are in smaller amounts. Air is natural. Nylon is synthetic. It's a material that is used in stockings, it's used in shirts, a lot of different things, kind of a slick feel to that material. Plastic, synthetic or not? It is synthetic. It is actually fossil fuel based, so it uses some natural materials as a lot of different products do, but it's synthetic. It is produced. Styrofoam, synthetic. Polyester, synthetic. Again, it's a material, it's used in a lot of shirts, and it's kind of a slick feel to it, similar to silk. Eggs, natural. Number 8, silk. Silk is naturally occurring. Silkworms can produce silk. Aspirin is synthetic. Carbon dioxide, natural. You breathe out carbon dioxide. You release CO2 as a byproduct of respiration and breathing. Coal, natural. It's one of our fossil fuels. Wool, natural. It is basically the hair of a sheep that is shaved off, and then it's produced into like string that can be woven into clothing. Water is natural. Cardboard, synthetic. Gold, it's natural. Paper, synthetic. And europium, it's one of our actinides, synthetic. Thanks, guys.